This is an introduction to waves, types of waves, wave properties, what waves do, what they don't do. So, wave characteristics. What is a wave? A wave is a periodic disturbance, usually in a medium, but we have the electromagnetic spectrum that are a bit special. They don't need a medium. Every other wave does. So waves are caused by something vibrating. It might be an object, it might be an electron in an atom, it might be atoms themselves, but something is vibrating and the energy of that vibration then passes out generally through the medium, but electromagnetic waves are different. So waves carry energy. Now, if we look at this animation, we can see on the left, we have something which vibrates up and down, which causes the wave. But you can see that the duck, whilst the duck moves up and down, it doesn't move to the right. So the energy is being transferred from left to right. But the medium itself, the water, all it does is move up and down. So we have some properties of waves. If we look at the water wave and we model that with a string, then you can see that as the wave travels through, the medium forms crests, peaks, and troughs, low parts. And there is this repeating pattern. The distance between one crest and the next, or one trough and the next, or here to here, or one complete peak and trough, that is one wavelength, and the symbol we use for that is lambda. It's a Greek letter. And what we saw with the water and what we were looking at here with the string, this is a transverse wave. There are two kinds of waves that we look at, transverse and longitudinal. And the transverse wave is the one where the energy was transferred left to right in this case, and the medium moves up and down. So the movement of the medium particles as the energy is transferred through is at right angles to the direction of energy transfer. So here we have another example, a wave in a string. The hand moves up and down. The particles of the medium move up and down. And the energy travels, in this case again, from left to right. So we've talked about the wavelength. The amplitude is how far a particle of the medium moves from this undisturbed rest or equilibrium position. Those three terms are used to describe the same thing. So the medium, in this case the string, is here before the wave arrives. And when the wave arrives, the particle moves up to here, so there's the maximum distance, displacement, that it moves from here. And this particle has moved down to here, so there's another maximum displacement from rest position. So there you have your amplitude. This distance here, or this distance here. It is not this to this. So we've talked about wavelength, distance between successive peaks or successive troughs. We've talked about amplitude, the maximum displacement from rest position or equilibrium position or undisturbed position. It all means the same thing. But the word equilibrium is important to get in there because we talk about equilibrium when we talk about forces, and it means the same thing. Frequency then is the number of complete waves made per second. So my top example is 1 wave per second, the middle one is 2 waves per second, the bottom one was 4. So we're doubling from here to here, and we're doubling again from here to here. And you can see that although there are more waves in the same space, the velocity of the wave hasn't changed. It's still moving at the same speed. And that's because the speed of the wave, or the velocity of the wave, depends on the medium, not the wavelength or the frequency. Which kind of makes sense if you think about sound waves. if sound waves travel at different speeds depending on their frequencies, then those different frequencies that you hear in music or in speech, they would arrive at different times. And so speech and music would be a very different experience. If high notes arrive before low notes, it would be very odd indeed. So the speed of the wave depends on the medium, the material it's traveling through, not on the frequency or the wavelength of it. Note the units, note that frequency is measured in hertz, that's the word with a lowercase h, symbol capital H small z. That's a common theme through physics, that if you're writing the unit in words, it is lowercase, but very often if there are two letters in the symbol, the first letter will be a capital and the second lowercase. So that's transverse waves, where the energy transfer is at right angles to the vibration of the medium. Here we have longitudinal waves, where the vibration, which is in this direction, backwards and forwards, and the energy transfer, which is from left to right again, are along the same line. They are parallel. And here, rather than having peaks and troughs, we have high pressure areas. You can see the turns in the slinky have been squished together, and low pressure areas where the turns in the slinky have been pulled further apart. This is a compression, and this is a rarefaction. It's an old word, but compression, rarefaction, high pressure, low pressure areas. And again, we use lambda for the wavelength, and the wavelength is the distance between the middle of one compression and the middle of the next, or the middle of one rarefaction and the middle of the next. We pick the middle because the middle is easy to spot, to be honest. It's hard to know where the compression ends and the rarefaction begins precisely, but you can pick the middle of the compression and the middle of the next compression quite easily. So that's why we pick middle to middle. And sound is an example of a longitudinal wave. And again, you can see how the particle of the medium, in this case, in one of the turns of the slinky, it doesn't get transferred, but it oscillates, so it vibrates from side to side as the energy travels through. And again, we have the amplitude, the maximum displacement from that rest or undisturbed position or equilibrium position. That is the amplitude of the particle in the turn of the slinky, or it could be a particle in air as the sound wave travels through. So, having talked about the two kinds of wave, longitudinal, where the oscillation of the medium and the energy transfer are parallel, and transverse waves, where the oscillation of the medium and the energy transfer are at right angles to each other. Having established that we have wavelength lambda, the distance between successive peaks, or the distance between successive compressions, we have the amplitude, the maximum displacement from that rest or equilibrium or undisturbed position, the frequency, the number of complete waves made per second. We then have a relationship between the speed of the wave, the frequency of the wave, and the wavelength. Now, we've already said the speed is fixed by the medium. So you would expect that as the frequency changes, so does the wavelength, so that the speed remains the same. And so it does. So the wave equation, V equals F times lambda, the wave speed is the wave frequency times the wavelength. That kind of makes sense if you think about it, because the wavelength is a distance, frequency is per second, and wave speed is meters per second, so there you've got your meters per second. So it makes sense to multiply those two together. If you think about it, if you have a wavelength of 2 meters and you make 1 wave per second, then the front of your wave has moved 2 meters in 1 second. If the wavelength is 2 meters and the frequency is 2 hertz, then the front of the wave has moved 4 meters in 2 seconds. So the speed being wavelength times frequency makes perfect sense.